This assessment asks us to draw the molecular orbital picture of ethanoic acid. We start this by assigning the hybridization to each atom. So this carbon has 3 hydrogens and 1 other carbon bond. It's going to be sp3 hybridized. An sp3 hybridized atom is going to bond using 4 sp3 hybridized orbitals. We can do the same thing for this carbon here. We have 1, 2, 3 areas of electron density. So it's going to be sp2 hybridized. And then as an sp2 hybridized atom, it's going to bond with 3 sp2 hybridized orbitals and 1 p orbital left over. It turns out this oxygen here, 1, 2, 3 areas of electron density, is also going to be sp2. That leaves only this oxygen here. Now, if we look at this oxygen, we've got 1, 2, 3, 4 areas of electron density, which might make us think that it's going to be sp3 hybridized. But recall that this lone pair of electrons can be delocalized by resonance and can be shared through resonance. That's going to give us a resonance structure that looks like this. And this resonance structure reminds us that this oxygen should be treated as if there are only 3 areas of electron density. 1, 2, 3 areas of electron density. So this oxygen is also sp2 hybridized, which means it bonds using 3 sp2 and 1 p orbital. With that, we're ready to start constructing the molecule. And we'll do this by keeping the carbons and the two carbons and the 2 oxygens in the plane of the page. So we can draw it like so. Here's our oxygen of our OH. We'll connect the oxygen up here like so. And then, of course, we've got the methyl group over here. We'll do the easy part first. Let's put the hydrogens on our methyl group. This carbon was tetrahedral and sp3 hybridized, so we need 1 hydrogen atom coming towards us and 1 going back away. So we can show that like this. We're done with the CH3. We've got the sigma bonds all shown. We can go ahead and put in the lone pairs on this oxygen, 1 of the lone pairs and 1 of the hydrogens. So we'll put that here. This lone pair is in an sp2 hybridized orbital. This OH bond is formed using an sp2 hybridized orbital. The last 2 lone pairs we have to show are these. These 2 lone pairs are going to be in the same plane as the CO sigma bond. At this point, we're ready to add in the p orbitals and the pi bonds. We'll start by doing it here, and I'm going to change colors just because the art is not going to be so great. But let's show a p orbital on this oxygen going out of and into the plane of the page. And we'll show this p orbital that it is bonding with coming off of this carbon, and we'll say that they're going to connect behind and in front of the plane of the page. So this represents the carbon-oxygen pi bond. Now, in terms of this lone pair here, the 1 lone pair we haven't shown, because of resonance, right? Because this lone pair, this is the one we haven't shown yet, because this lone pair is in resonance with the carbon-oxygen double bond, it's in resonance with the carbon-oxygen double bond, for us to have that overlap, it needs to be in the same plane as the p orbital. And so we'll show that lone pair as being here. I'll dash most of it, but let's stick that lone pair there. That shows that this lone pair is aligned with the pi system, which is why we have resonance happening, or that's a consequence of the fact that resonance structures can be drawn for carboxylic acids. This is the molecular orbital picture of ethanoic acid.